This meeting is being recorded.
In section 6 of chapter 16, we're introduced to a new reaction type called pericyclic reaction. So we've seen in the past reactions that occur with ionic intermediates or free radical intermediates, but we have not been introduced to this class of reaction called pericyclic reactions. And we'll see that within these there are three main types of these pericyclic reactions. So the first type we'll see is what's called a cycloaddition. So we see, this structure over here, this butadiene with this structure over here being added together. So that's where the addition comes from, and we form a cyclic structure as a result. So we have this cycloaddition. The second type is an electrocyclic reaction where the electrons are rearranging to form a cyclic structure. So we see through three arrows here, movement of three electron pairs, redistribute those electrons to form this cyclic structure on the right. Then we have our last form of a pericyclic reaction, or last example, is a sigmatropic rearrangement where our sigma bonds are rearranged, right? So this sigma bond here is now over here. So let's take a look here at some of the common characteristics. So each of these pericyclic reactions has four characteristics in common. The reaction mechanism is concerted, so there are without any intermediates, so no intermediates, hence why this is a different type of reaction than we saw with those radical and carbocation intermediates. And then we have our second characteristic feature here. The mechanism involves a ring of electrons, hence the cyclic part of pericyclic. So we end up with a ring of electrons moving in a closed loop system. Then we also have our transition state in the third characteristic here. It will be cyclic for all of these types of pericyclic reactions. And last but not least, in number 4 here, note that the polarity of our solvent really doesn't have an effect on the rate of the reaction because our transition state, as we noticed earlier, is cyclic, and it would really have little, if any, charge. So that's why our solvent polarity really does not contribute to an effect on rate. So distinguishing pericyclic reactions, one from the other, we can see down here in our first type, the cycloaddition reaction, we see the number of sigma bonds to start changes by 2, right? So whatever we have to start, we're going to add 2 sigma bonds and then subtract 2 pi bonds. So we're going to always have a change in pi bonds and sigma bonds to distinguish our pericyclic reaction. So cycloaddition, up 2 sigma bonds, down 2 pi bonds. In our second type of reaction here, our electrocyclic reactions, we're going to increase again the number of sigma bonds, but now we're going to increase by 1, and then we're going to decrease pi bonds again, but just by 1. So when we have up 1 sigma, down 1 pi, that's an example of electrocyclic reactions. Last but not least, we have with our sigmatropic, we know that a reaction has occurred. We know that there's movement of those sigma bonds within our cyclic structure, but our net result is neither an increase nor decrease in the number of sigma nor pi bonds. So we would net a 0 change in both. So we'll look at a specific type of cycloaddition reactions in section 16.7.